First of all, I would like to thank all those who are present to stay until the very last topic of today, because I know it's really a challenge to listen for such a long time. The topic today, this very final topic, is in a way complementing the very first talk that we heard on Monday morning. Joseph talked about making embedded systems correct. I think they have to be both correct and efficient, and today I'm trying to cover the aspect of efficiency. It's also covering some other talks like Nani's talks and Luca's talks, which have been trying to make embedded hardware and hardware for cyber-physical systems efficient. I will be more talking about making software efficient for these systems. The motivation for my talk is very similar to the one that we had already as a motivation for the other talks. We know, according to several forecasts, that the future of information technology is characterized by the integration of computing into many technical products. So we know that, for example, in cars we find more and more electronics, in planes and in trains we find more and more electronics to make them safer, to make them more energy efficient. And we also see the same, obviously, in robotics, where more and more information processing is going on. Before going into the details, I'd like to make sure that we have a clear view of the terms that we're using. Many people are talking about embedded systems, and people sometimes have a different impression of what it really means. Therefore, I'd like to refer to a definition which I wrote down in a textbook about 10 years ago. I wrote information processing embedded into a larger product is what we call an embedded system. So there we are referring to one of the words which is used in the term, and I think that's only natural to define it in that way. Then sometimes there is the confusion of what actually is a cyber-physical system. There I like to refer to some of the articles which Edward Lee wrote some years ago, about 5 or 6 years ago, where he described the integration of computation with physical processes, and I think this is what we could call a cyber-physical system. In this definition, I don't have the networking aspect that was mentioned yesterday by Alberto. So I think it's a little bit subject to discussion whether we really need the networking there. I think the networking is included there because people would like to have the Internet of Things included in that definition, and therefore they are stressing networking. In a somewhat simplified way, we can say, well, cyber-physical systems comprise the physical environment and the embedded system that's performing the information processing. So we also learned yesterday that cyber-physical systems are to be designed in a multidisciplinary way, and therefore I believe that the walls between the many disciplines that are involved have to be torn down. So the walls between computer science, electrical engineering, obviously physics, also statistics, mechanical engineering, they have to be torn down. And I'd like to make this talk at least a little interactive by asking you if you could identify a problem on this slide. Would you see any problem with this slide? Pardon?
Nobody working on this side of the medicine statistics.
Nobody working there. Okay, that's a little generic because I couldn't put too many walls there. Yeah.
They're working on different sides.
They're working on different sites. Yeah. Nobody's coordinating. Yeah, maybe if finally they would succeed, it would be something, even if it would be uncoordinated. But let me tell you what I consider to be a problem with this slide. I'm watching this slide for quite a number of months, and there is no progress. So everybody is pretending to work, but there is no progress. Yeah, so it stays the same situation. So cyber-physical design should be multidisciplinary, and I think that was also obvious from Nani's talk just previous to this one. The fact that we are integrating computations with the physical environment has quite some consequences, and I think maybe the most important consequence is the fact that we have to consider timing. time is a very important physical quantity, and we must take into account that we are connecting our computational devices to the physical environment, and therefore we have to refer to the timing. So we have to react within the time interval that is dictated by the environment, and in this formulation I'm adopting a certain citation from Berger when he defined the term reactiveness. In my view, it's sufficient, or for the applications that I'm considering, it's sufficient if we are imposing an upper bound on the execution time. So I'm not really requiring also a very tight lower bound or just a single value for the execution time. For the systems that I will be considering, it's sufficient just to have an upper bound there. The fact that we have to consider timing has consequences which, from my point of view, are very frequently underestimated. So, for example, people are not really realizing that they have to raise the question whether certain off-the-shelf components can really be used in a real-time system. So, for example, the fact that we are using caches whose effect at runtime can hardly be predicted, I think that leads to the question whether we should possibly redesign some of the systems. Also, specifications are very poor when it comes to a specification of the timing. Also, and there I'm referring to one statement made much earlier by Hermann Koppitz, also we have to respect this timing always. It's not sufficient just to respect this in 99% of the cases. We have to respect this always, because we are working possibly in a safety critical environment, and there it's not sufficient to have a number of experiments and from the number of experiments to conclude that the likelihood of a failure is below a certain threshold. That's certainly not sufficient. Recently there came up a discussion in this relation about very small probabilities. If we had very small probabilities that were orders of magnitude less than the probability of the system failing anyway, then possibly we could tolerate these extremely small probabilities. Second requirement, which is resulting from the fact that we have this link to physics, is the fact that very frequently we have to consider energy constraints. These systems are frequently mobile systems that we are carrying around, and there are essentially two potential sources for energy. We could do energy harvesting, or we could have batteries. Now, for the systems that I'm considering, I'm not talking about energy harvesting. The amounts of energy that are available there are still very slow, so therefore I'm mainly looking at systems that have to be energy efficient because they are using batteries. But what we are going to say about these systems would also apply to systems that are using energy harvesting. Again, I believe that the frequency, that the consequences of this requirement are very frequently underestimated, because people tend not to really consider the fact that we need energy to perform a large number of computations and to have a very computational demanding job there. So, for example, one of the potential consequences is the fact that we need to use heterogeneous processes. A number of implementation aspects would be easier if we could constrain ourselves towards homogeneous processes. However, it has been demonstrated that we achieve maximum energy efficiency only if we use tailored processors, some processors that are optimized for a certain function, and only with these processes are we able to come to this, what I call the sweet spot of this energy efficiency diagram, the sweet spot where we are pretty close to the maximum that can be achieved with silicon technology, the maximum that can be achieved with application-specific circuits. So, for example, for the Nexperia platform, it has been demonstrated that we achieve an energy efficiency around 66 giga operations per watt, which brings us really to the sweet spot of the diagram, and obviously with the other technologies we would be in other areas of the diagram, but not in the sweet spot where we have to be for these demanding applications. So that is one of the consequences that is the result of being energy constrained. There is a third requirement resulting from the fact that we have this tight interface to the physical environment, and that is the fact that our systems must be reliable. Because if our systems are performing not correctly, then we might have negative consequences there on the environment. We might cause damages, we might cause harm to people. So therefore, these systems must definitely be reliable, and therefore something like the Titanic is just illegal. Again, the consequences are frequently underestimated. We have to make sure that we achieve failure rates that are in the order that is specified for safety critical systems. You learned on Monday that, for example, there are these SIL levels which require that we are in the order of 10 to the minus 9 failures per hour, which is indeed a very small number. This number actually leads to the definition of one unit which is used in this context. It's a unit called FIT, which also denotes failures in time. One FIT corresponds to one failure per 10 to 9 hours. Now, if you look at the failure rates for integrated circuits, you will find that it's very difficult to find concrete numbers there. And that's for good reasons, because the circuit manufacturers will normally try to hide these numbers from you. If they were available, they would be trying to hide them from you because they indicate somehow the quality level for their manufacturing process. So therefore, you will hardly get access to these numbers. This is, in fact, the only diagram that I found so far. And there you see that for something like 2,000 or 5,000 hours, we will be staying below this failure rate of 1 FIT. But then if we have more operational hours, then we will get failure rates in the area of 100 to 1,000 FIT. Now, obviously, if we would like to design safety critical systems out of these devices, we need to use redundancy, because otherwise we will not stay below 1 FIT. There may be the question, how do we actually get these numbers? Because we are talking about a very large number of hours there, and how do we test these devices for the failure rates for such a very long time? It is not really possible. So the way that is usually taken in this case is to test a large number of devices at increased temperatures, and then there is an assumed relationship between failure rates at higher temperatures and at lower temperatures, and therefore these failure rates are then typically derived from the failure rates at higher temperatures. Otherwise, it would be impossible to wait for example, 10 to 10 hours. That's beyond our normal lifetime. So that's how we arrive at these numbers. So these are the three aspects that have to be taken into account when we design cyber physical systems. At least these three aspects have to be taken into account. But in general, many different aspects have to be taken into account when we design cyber physical systems. So we are talking about the worst case delay as an objective there, but the average case delay and the resulting average performance is also important. We're talking about the power consumption and the energy consumption. Reliability was mentioned as the third objective. Linked to that, we have the thermal behavior, we have safety and security requirements, we have cost and size evaluations, we have to look at the weight, we have to look at electromagnetic compatibility, at radiation hardness, environmental friendliness, extendability, etc. So as there is this huge set of objectives that we have to take into account when we design cyber physical or embedded systems. This very naturally leads to the consideration of Pareto optimality, and in this context it's my pleasure to refer to a book in which this is very nicely described. This is a book that will be passed around. That's a book that can be used as a textbook just in case you need a textbook to get an introduction to embedded system design and some of the fundamental techniques here. Okay, so this brings me to the outline of my talk. I have finished the motivation and the introduction, and next I'm going to talk about timing. Then after a brief break I will talk about energy as an objective, and in the final section I will also talk about multi-objective optimization, and finally there will be a summary. So let's look at timing now. First of all, I'd like to make sure that you understand the important terms in this context. I'd like to make sure that especially you understand the term worst-case execution time. If you monitor the execution times of applications, you will realize that there are certain execution times that are more frequent than others, and among all the execution times there is one execution time which is the smallest, and this is what we call the best case execution time. On the other hand, there is also the largest execution time, which is called the worst case execution time. Now, unfortunately, in most of the cases, it's not really possible to compute that worst-case execution time. In most of the cases, we have to be happy if it's feasible to compute a good upper bound on that largest execution time, and that good upper bound is called the estimated worst-case execution time. The fact that we are using the term estimated there doesn't mean that it's somehow unreliable or not precise. We will be requiring that this estimated worst-case execution time is actually a safe estimate, so it should never be less than the really feasible largest execution time. Also, we require that this estimated worst-case execution time is tight. That means the difference between these two numbers should not be too large. Typically, we will require that this estimated worst-case execution time does not increase the deadline that I mentioned earlier. Now, how do people design systems for which there is a worst-case execution time, or for which there is a deadline? Well, the typical procedure that I'm sketching on this slide is starting, hopefully, with a specification of the cyber-physical or embedded system. And then from the specification, there should be some generation of code. So maybe we're using model-based design. So using model-based design, we are generating some code, maybe C code, for example. And this code is then compiled using some compiler for our target processor, and then we are having an experiment in which we are trying out whether this software is actually running at the required speed. We might be doing that using simulation. We might be doing that in a real system. Alberto mentioned yesterday that somebody will grab a board, download the software onto the board, then connect it to the real system, and very likely will observe that the initial software doesn't meet the real-time constraint. So things like that will be done during this fourth step. There is a very serious question of which input data we are going to use there, which input data will lead to the largest execution time, and which would be the initial state from which we are starting there. Watching these experiments, we will be measuring the execution times, and among all those execution times, one will be the largest, and this is what we call the measured worst-case execution time. Now, we are not really sure whether that is really the largest feasible execution time, so typically designers add some safety margin, M in this case, on top of that measured worst-case execution time, and call this the hypothetical worst-case execution time. And then this hypothetical worst-case execution time is checked against the deadline, and if we are violating the deadline, we have to start all over again. We might have to change the specification, we might have to change the software, we might have to change compiler options, so that's what we need to do there. I see a couple of problems with that approach. First problem is the fact that this is not a very dependable approach, because this hypothetical worst-case execution time is not a safe approximation. We don't know whether we really have used the worst-case input data. So therefore, when we use that system, the time constraint might indeed be violated, even though the designer has checked for that violation. Second problem is the design time. because, as already mentioned, we will have to change some detail of the input to our design procedure, and it is a question, how do we find out where we would need to change the input, how many iterations are actually required there. So we could be running around in the cycle for quite a number of times, and some designers might actually fall off that cycle because they give up at a certain point in time. Then the whole design procedure is based on making the common case fast. This is what is recommended by computer architects. If you read the book by Hennessy Pedersen, for example, they tell you that it's very important to make the common case fast. Now, if we make the common case fast, we can have a distribution like that one, where we are trying to look at this common case, and we see immediately that for real-time systems, this is not a sufficient approach, because we have to make sure that the worst case is sufficiently fast. Circuit designers know that making the common case fast is not sufficient, but computer architects, at least until recently, were not really well aware of that. Compiler designers also are not aware of that, because typically their goal is to make the code fast. They don't really know what that really means, and they don't really know how to figure out what would be the worst case. Actually, we have a rather poor situation in compiler design these days, because frankly compilers are hardly capable of figuring out any values of cost functions. They could possibly compute the resulting code size, but compilers these days have no knowledge of any execution time model. 30 years ago, when you read an assembly language manual, there was an execution time attached to each instruction. These days are over, and therefore there is no timing model in currently available compilers. So if you talk about an optimizing compiler, you might question what they are actually optimizing for. So therefore, we need to look at contributions that try to help us to solve the problem. One contribution in that area is the use of predictable hardware architectures, like the PRID architectures that Edward Lee is working on, but that's currently an exception, and that would require in many cases to change many of the available hardware components. So we would possibly not be able to use off-the-shelf components. Then, of course, we can try to use predictable operating systems. You may have heard about time-triggered operating systems as proposed by Hermann Koppitz. That is certainly one contribution that we can use. Then we can ask for modified algorithms. We can modify algorithms so that we have the same execution time for all data. That, in fact, may be necessary for security reasons. You know this, for example, in certain safety-relevant areas where it's important that people are unable to figure out which code is actually the correct one. There we need to have algorithms that always execute with the same execution time, but in other areas I think this is going too far. Then we can look at the design of formal worst-case execution time analysis tools, and we can try to integrate compiler design with worst-case execution time analysis tools, which is what I will be looking at a little later on. Right now, I would like to provide you with some fundamental knowledge about the computation of these upper bounds. I think this is knowledge that may be very useful if you look at the design of real-time systems. So let's look at how this worst-case execution time estimation is currently performed. I am using there one of the leading tools in this area as an example. A tool called AIT has won a couple of years ago the European ICT prize, because that was the best tool that's available for worst-case execution time estimation. It's available from a spin-off of the University of Saarbrücken. For this tool, we start with an executable program. That is very essential, because from a high-level program we cannot really estimate the worst-case execution time. From this executable program, we are constructing a control flow graph. And then to this control flow graph, we apply a certain number of loop transformations. So typically, for example, loops are unrolled once, because the timing behavior of the first iteration of a loop is frequently completely different from the timing behavior of the other iterations of the loop, because you might first load a number of caches, and when these cache lines are loaded, execution is faster per operation of the loop, so therefore we apply these loop transformations. As a result, we get some information there about the basic blocks that are used in the program. And then for these basic blocks, we are performing static analysis that is based on abstract interpretation, which is a mathematically comprehensive technique that allows us to narrow down the possible values that could be held in memory and in registers. As a result of that, we get some predictions for the cache and the pipeline behavior, and we get precise upper bounds there or we get good upper bounds there for the largest execution time for each of the basic blocks. This is then stored in a file and forwarded to path analysis, where path analysis has as its aim to figure out what is the largest worst case execution time overall for the entire program, assuming that we know the worst case execution time for each of the basic blocks. And this is done by mapping this problem to an integer linear programming problem. We are using an integer linear programming solver there, and then we are evaluating the results, and we can visualize the resulting worst case execution time. In general, it's not feasible to derive all the loop bounds automatically, so some help by the programmer may be needed to annotate the program so that we have more knowledge about the loop bounds. Now, using the next slide, I'd like to tell you how this path analysis is being performed, because I think there is a nice trick involved. Until the 90s of the last century, designers have assumed that they have to enumerate all the possible execution paths in order to compute the largest execution time. Now that would be very inconvenient, because the number of execution paths is exploding exponentially with the size of the program. So that would be very demanding. But it turned out that this is not feasible, this is not required, because there is a nice trick, and I'd like to demonstrate that trick. For this trick, we start with a program, and this program is converted into a control flow graph. So this is the node corresponding to the main program. That's the node corresponding to the test of the for loop there. This is the node corresponding to the test of the if statement. And these are the nodes corresponding to the then and the else part. And this is the code that we execute before we start the next iteration of the loop. And this is the code that we execute before we terminate the program. So in order to compute the worst case execution time of this little program, we are doing the following. First of all, we are running this worst case execution time estimation for each of the basic blocks. And we can use, for example, AIT for this. And for the tri-core processor, which is a very popular processor in the automotive industry, this tool would find the number of cycles that are indicated in this little table over here. So that's the largest execution time that's feasible for these corresponding blocks. Now the next task is to use this information to derive a global worst case execution time. And the nice trick is the following. We are mapping this problem to an integer linear programming problem, where we are using the execution time as the cost function or objective function. So for example, we have 21 times the number of iterations of the main program as the execution time for the main block of this program. And we have 27 times the number of executions of this block labeled L1 as the contribution there of this block L1 to the overall execution time. And this continues on for all the other blocks. So the different terms are the terms for each of these blocks. Now the overall goal is to maximize this function, and if we have computed the maximum of this function, we have computed a safe upper bound of the execution time. Now the remaining part of the problem is to constrain the values of these variables such that we are reflecting the structure of this control flow graph. Now this is actually very straightforward because what we are doing there is a little similar to Kirchhoff's equations in that we are exploiting the fact that the number of executions of this block L1, for example, must be equal to the number of times that we are branching into that block. So therefore x7 minus x8 minus x6 must be equal to 0. And also the number of times that we are leaving that block must be equal to the number of times that we are executing the block. So therefore x7 minus x9 minus x10 must be equal to 0. So in this way these constraints are reflecting the structure of this control flow graph. The nice trick in this case is that we are avoiding an explicit enumeration of all the possible paths. So otherwise we could be confused by the large set of paths that would be feasible in this program, and this confusion is avoided by this mapping to this ILP problem. Okay, in this way we compute the worst case execution time for that particular program. It's 6,268 cycles, and we also get some information about the iterations that correspond to that worst case execution time. Now from my point of view, this is not really sufficient because we are computing this worst case execution time only after we have generated the code. Now I already mentioned that compilers these days hardly have any information about the execution time, so therefore we have proposed to make compilers aware of the worst case execution time and to actually optimize for the worst case. And this is feasible if we integrate AIT and a compiler. The right-hand side of this slide shows our integration of AIT and a compiler. Fear not, this is less complicated than it looks. So it's a complex structure of a compiler where you start with the source code that you use as input there. The source code is parsed. Then you represent the source code at a very high level. You have a so-called code selector which maps this source code to machine instructions. You represent them at a lower level, and then you have some post-processing that finally generates the assembly code. Now, in order to have a compiler that can optimize for the worst case, we connected this compiler to AIT, and it turned out that this was actually not that complicated because for AIT we need an abstract representation of the basic blocks, and this is what we actually had available there in the compiler, so we only needed to convert the different formats, and after an execution of AIT we got the information about the worst case execution time for each of the blocks, and this is now key for enabling optimizations that take the worst case execution time into account. You can do this at a lower level, but we also have back annotation, and using back annotation we can make that information also available at a higher level. So just to demonstrate one of the problems that we had to solve in this context, one of the essential problems is that if you optimize for the worst case, you have to know what the worst case is. That means you have to know the worst case path in your program. Now, unfortunately, the worst case path in your program can change for every transformation that you apply to your program, which would mean that you would need to recompute that information quite a number of times. And now AIT is not a very fast tool. So if you need to recompute that worst case path a number of times, that may be rather time consuming, so therefore you have to be a little careful there. So when we started this work, we found ourselves to be in a very nice situation, something that happens to you in a professional life typically only a limited number of times. Because when we started, there were 1 or 2 master theses available in that area and nothing else but that. So we could essentially structure this area ourselves, and we could, try to find where new optimizations would be most promising. What we essentially did is we were able to reconsider all the compiler optimizations with respect to their impact on the worst case execution time. So you can have a fresh new look at everything which is written in a standard compiler textbook. So therefore we came up with quite a number of new optimizations or optimizations that were taking worst case execution time into account. First of all, we had to extend the loop analysis that was provided with AIT because we needed some smarter loop analysis. Then we looked at instruction cache locking. That means we have been loading certain information into instruction cache and then locked the cache so that we were sure what's actually there in the cache. You can also look at cache partitioning. That means, for example, you can figure out what should go into one particular way of the cache and what should go into another particular way there in the cache. You can look at the procedure cloning because you can have cases where you have conflicts in the cache that are resulting from the fact that procedures are called from different call sites. So if you clone procedures, you can possibly avoid that. You can also position procedures and code in the address range, in the address space, in such a way that you reduce the conflicts there in the caches. You can use function inlining. Function inlining is an optimization that typically is not based on any knowledge of any objective function. So if you have that knowledge available, it's very useful. Then you can perform loop unswitching. This means that you move if statements out of loops. We will briefly look at loop unrolling, and there's a couple of other optimizations that you can also look at. So this is our result of having a fresh new look at standard compiler optimizations. As an example, I would like to look at loop unrolling. For loop unrolling, we have a very interesting situation in that for loop unrolling, we are applying a compiler transformation very early during the code generation. We are hoping for the positive effects, so we might have a reduced overhead for loop control because we have a reduced number of tests to perform. In many cases, we are enabling instruction-level parallelism because we just have more code in the loop body, and in this way we can keep all the functional units busy in a much easier way. And in many cases, loop unrolling also enables following optimizations. For example, we can detect more common sub-expressions. However, as I said, loop unrolling is done very early in the optimization procedure, and therefore it's very difficult to predict possible negative effects. Like we can have unrolling to a level where we have thrashing for the instruction cache, and as a result of that, loop unrolling could make the code slower. Also, if we unroll the code, we are ending up with very long sequences of straight line code. As a result of that, we can have a large amount of live variables, and as a result of that, we can have additional spill code where we spill values to the memory. And also we might need additional control codes, for example, in the case where we have an uneven number of loop iterations. So the problem there is that the consequences of this transformation are hardly known. If you use loop unrolling as a user of a compiler, you typically specify certain heuristics. You're running experiments with these heuristics, and you hardly ever know what the impact of these heuristics is. So in our case, we exploited the fact that WCET information was available at the assembly level. However, we had to take into account that this optimization is performed at a very early phase, so therefore we had to use back annotation. That means we have to make sure that this information is propagated to the high level so that when we perform this optimization at the high level, we know the impact on the quality of the code. What we are propagating there includes the worst case execution time data, the assembly code size so that we know whether we would be going beyond the size of the instruction cache, and the amount of spare code so that we know whether we are generating a lot of spare code or not. And also we need to have some knowledge about the memory architecture. We need to know how large is actually the instruction cache. Now the results are shown on this slide. You can see that for the various sizes there of the instruction cache, we have reductions of the worst case execution time to less than 90% of the original number. And we can see that we have reductions between about 10 and 15%. So on the average, this loop unrolling outperforms standard loop unrolling by 13%. So that means something has been achieved. The PhD student who did this work was actually proud of having achieved these 13%, because when you work on compiler optimizations, you have many cases where you improve the speed only by a few percent. But frankly, this was not what I expected, because I personally expected that for loop unrolling we would have a higher effect, because loop unrolling is really not relying on any information about the runtime, so it is just guessing, and we could have expected to have a larger effect there. But this is how it's like in science. Sometimes when you study certain effects, sometimes the effects are smaller than expected, and sometimes they are larger. We will see that there are also cases where they are larger. So as a second case of what we did in this context, I'm considering superblock optimizations, which means that we are now not just considering single basic blocks, but sets of basic blocks. And there we are studying standard compiler optimizations such as common sub-expression elimination and dat code elimination. So there you see that if we combine the superblock-based handling of common sub-expressions with this information about worst-case execution times, we can indeed decrease the worst-case execution time, the estimated worst-case execution time, by certain numbers. There is one case which is really good, where we could reduce the worst-case execution time by more than 40%. So that was the second example that I am demonstrating in this presentation. This is a third example, which is referring to the locking of the instruction cache that I mentioned earlier. In this case, you try to compute already at compile time which instruction objects you would like to have in the instruction cache. Then you're loading them into the instruction cache, and then you're locking the instruction cache, so that there is no automatic replacement anymore. The key advantage in that case is a very excellent timing predictability, because you know exactly which instructions will be loaded from the cache and which instructions will be loaded from the memory. And you can see that in this way it's really feasible to reduce the estimated worst-case execution time significantly. You see that for larger caches we can reduce the estimated worst-case execution time by more than 50%, which is, I think, a pretty good number, and actually larger than what we achieve in the case of this loop unrolling. There is one other study where we looked at register allocation. We know that registers are the fastest elements there in the memory hierarchy. Register allocation tries to assign registers to the different variables that we are using there internally in the compiler. And this allocation is typically based on conflict graphs. There's a very simple case shown on the slide where you see that we are starting with the lifetimes of the variables and looking at whether or not these lifetimes of the variables are overlapping. We find that we need to allocate different registers to V1 and V3. And the same goes for V2 and V3, but V1 and V2 can possibly share the same register. So what the compilers are typically doing in this context is they are generating such interference or conflict graphs, not necessarily based just on basic blocks, but possibly doing this globally for the entire code, and then coloring these graphs. That means they are assigning colors so that any two nodes connected by an edge are obtaining different colors. Now this is what we also did for this compiler that's aware of worst case execution times, and there, to my surprise, we found a very good decrease of the worst case execution time, because there was only one case where the decrease was rather small, but there was one case where the decrease was really substantial, and on the average this was a reduction by over 30%, which I think is pretty good. The question may be what is actually being done there. In this case, the corresponding student did modify this graph coloring in such a way that for all the decisions taken there, the consequences in terms of the impact on the worst case execution time were actually considered, and in that way it was feasible to reduce these worst case execution times substantially. There are more optimizations that can be considered in that context. So, for example, another student looked at potential cache thrashing. You might have a situation where from one function you're calling two other functions, and it could happen that these two other functions called foo2 and foo3 are actually placed in the address space in such a way that they compete for the same entries there in the cache. Now, this can very easily happen, and if it happens, it's actually better not to cache one of the functions at all, because in that way you avoid all these conflicts there for access to the cache. And this is what Sasha Plaza did during his PhD thesis, and in this way he avoided all the conflicts by allocating certain functions to some uncached area there in the memory, in this way avoiding all the conflicts there for the instruction cache. And these results show that indeed it is feasible to reduce the worst case execution time in this way. You see that for different sizes of the cache, there was a reduction of the execution time by between a few percent, and in this case about 20%. These were a number of optimizations that were performed. Additional optimizations were performed for so-called scratch pads that were already mentioned during the summer school a number of times. Now, just to make sure that you understand the concept of scratch pads are rather small, physically separate memories which are mapped somewhere into the address space of our system. A key distinction between scratch pads and caches is the fact that for scratch pads we don't have any tag memory. Whether or not we have a reference there to the scratchpad memory is based on looking at some of the more significant bits there of addresses, and when we have the right values there, we are generating a kind of chip select signal there, which then enables the scratchpad memory. And there are many systems that do come with a scratchpad memory. We have seen yesterday, for example, that the processor that Luca Bernini designed involves a scratchpad as well, and ARM processors allow you to have a scratchpad. So that means scratchpads are interesting. From our point of view, they have three nice features. The first feature being the fact that they are fast because they are small. The second feature is that they are energy efficient for the very same reason, because it requires less energy to access a small memory. And the third feature is the fact that they are timing predictable, because we use them usually in such a way that already at compile time we know whether or not we have an access there to the scratchpad memory. So we did use these scratchpads also for WCET-aware memory allocation, and we did this for a larger example because we wanted to get rid of just looking at some academic toy examples. So therefore, in the Predator project, in which Lothar Telescope was, for example, also involved, in the Predator project, we got from our industrial partner Bosch a so-called demo car software. Demo car software is software which is modeled after the software which is controlling the engine in the car. It is not the original software which Bosch is actually using for their customers, because that software is top secret and would never leave the premises of Bosch. So therefore it was a kind of modified control software for the engines. In this case, our experimental worst-case execution time aware compiler did this allocation of objects here to the scratchpad memory that are available for the tri-core processors, and we were able to reduce the worst-case execution time to about 50% compared to that what's feasible with GCC. So as a result, the industrial project partners there were interested in playing around with that compiler, because they wanted to know what is actually the potential of this compiler technology. Can we use this to cut down the number of control processors in cars by 50%? That would of course be very nice. Could we possibly use slower processors there in the car? Both would save a lot of money. Working on the allocation to scratchpad memories, our students also went on and looked at systems where we are having several tasks instead of just a single task. So therefore, it was considered how we could allocate the different memory objects in the address space in such a way that we have certain areas there for the different tasks in the scratchpad. So that we would have one area where we have objects there for task 1, another area where we have objects for task 2, and another area there for task 3. And we can again demonstrate how we can reduce the worst-case execution time for this scratchpad-based system. We can see that by using this worst-case execution time aware compilation, we are able to reduce the worst-case execution time by about 30%. And there are certain differences between the different heuristics. In this case, it turns out that it's best to use the heuristic that is actually considering the worst-case execution time and not just the code size heuristic. In other cases where you would not have available this information about the worst-case execution time, you would need to use the code size as an indication of what should be migrated to the scratchpad, and that seems to be not a very good idea. These are two other results that also demonstrate by how much we can reduce the worst-case execution time by making the compiler aware of that objective. So this brings me to remind you, this brings me to this situation to remind you of the overall structure of this talk. We did, of course, finish the motivation and the introduction, and I talked about timing, I talked about worst-case execution time estimation, and the integration of this estimation into compilation. So at this point in time, I suggest that we have maybe 5 minutes for questions about this work, and then we have maybe 5 minutes of break. And then I would start the second part of this presentation.
Do you have questions?
Do you see possibility by using compiler technology also to, even if the architecture is by default compiler is unpredictable, but just have some restrictive use of it and then making it predictable? For example, we've seen yesterday an architecture where the conflicts access to banks. So, but if you compile such that every processor accesses to a separate bank, then there will be no conflicts. Such things, did you see in the work compilers?
Yeah, so the question is, could you use compilers to make architectures more predictable if you take compilation also into account? I think that is indeed feasible. So we have demonstrated this already, because for caches you have these inherent conflicts for the use of certain lines there in the caches. And if you allocate your objects in a smart way to the address space, you can reduce the number of conflicts. So in that way, you can make caches more predictable by a smart use of the address space. And a standard compiler would not do anything in that direction because, I mean, the addresses that are used there in compiled code depend on the order in which you write down the functions there in the source code. Now that may be the most stupid order that can be selected because by just reshuffling the functions there in the address space, you can reduce the number of conflicts there for the cache and in that way make your system more predictable. Yeah. But you cannot remove all sources of unpredictability. If there is something that is very difficult to predict by the compiler, then of course there are limitations to what you can do. Yeah.
Yeah. Suppose this applies to monocore. You don't consider the multi-cores and the interactions and so on. So now, if we are in the assumption of monocore, how do you deal with executions that depend on the values of the data that you receive? That means that all the ifs won't give always the same maximum values. It means that you cannot predict clearly how long it will take.
It's right that this is kind of a standard material. Some of this is rather recent, but some of this is rather standard material where the work was initially constrained towards the use of single cores. Now, we have students that also work on the issue of multi-cores. However, it turns out that there it's, first of all, very important that you remove some of the sources of timing unpredictability. So I have one student, for example, who works on analyzing the resulting response times if you have a TDMA bus. But if in a multi-core you have a priority-driven bus, then you have a source of unpredictability, and that is very difficult to remove. So in the compiler itself, I think there is very little that you can do for multi-cores, for timing predictability of multi-cores. But of course, you have to invest some work into the analysis of possible timing behaviors if you do indeed have multi-cores. And I think at this time it was very important that a number of researchers, including Lothar, for example, have been trying to press industry to really look at timing predictability when they design their multi-cores. Because if multi-cores are designed in a timing unpredictable way, there is very little that you can do in the tools. Yep. And we have seen from Luca that he was also concerned with the timing predictability.